Hello, chemist and biochemist. This is the last video where I'm going to talk about different types of inhibition. Now, these last two types of inhibition, you'll commonly see them grouped together. The types of inhibition that I'm going to talk about today are your mixed inhibitors and a non-competitive inhibitor. They're commonly grouped together because they have lots of similarities to one another. Now, with that said, I want to go ahead and get into our discussion of them. So the first thing that I'd like to do with respect to these two is I'd like to really just kind of introduce them. Mixed, and I'm going to label the non-competitive as NC. Okay. Now, one thing that makes these two types of inhibitors present or similar to one another is if we follow the E plus S yields ES complex plus, or sorry, yields P plus E. If we follow that scheme, well, this is really helpful, I think, whenever you're discussing what do different types of inhibitors bind to. Now, in the case of a mixed inhibitor and a non-competitive inhibitor, this is where they're most similar to one another. Well, what they both are able to do is they are both able to bind the free enzyme and the enzyme substrate complex. So what that means is they have similarities of both a competitive inhibitor and an uncompetitive inhibitor. Because with a competitive inhibitor, you form this EI complex. So the enzyme plus the inhibitor form one complex. Whereas with a uncompetitive inhibitor, you form this ESI complex. And with a mixed or a non-competitive inhibitor, you're going to form EI and ESI. Now, what's worth noting about this is that and I would say the biggest difference between a competitive inhibitor and a mixed and a non-competitive inhibitor is that this inhibitor right here is binding in a site other than the active site of the enzyme. Okay, so this inhibitor right there will bind to some location other than the substrate binding site. Okay, now both the mixed and non-competitive inhibitors will form EI and ESI. So they both are capable of preventing the formation of your product. Now, our other factors that are worth noting are really something that revolve around our double reciprocal plot. Now, our double reciprocal plot, known as the Lineweaver-Burke plot, takes our Michaelis-Menten plot and makes a, well, linear representation of that data. Our y-axis is 1 over velocity, or our initial velocity, and our x-axis is 1 over substrate concentration. Now, I've drawn our axes in red, and I'm going to draw one line which corresponds to a data set where no inhibitor is present. And whenever you have a plot like this, there are some things that you're able to figure out. You're able to figure out, well, negative 1 over km is equal to your x-intercept. Your y-intercept is 1 over V max. Now, I personally always like to play around with numbers. I always like to plug a number in so that I can do the simple calculation to figure out what is that km, what is that V max. And what I've seen people do over the years is they run into negative 1 over km, and they tend to forget that this x-intercept is a negative value. So they'll make a mistake and they'll end up with a km that's, a negative value. And that's simply something that's impossible because a km is a concentration. It has to be a positive value. Now, I'd like to go ahead and draw two other lines. These lines are going to correspond to the impact that a mixed inhibitor or a non-competitive inhibitor will have. I'm going to draw a non-competitive inhibitor and represent it with a green line. When you use a non-competitive inhibitor, it would be common to see a data line or a data set that gives you a line like this. So this is plus NC. Now, what I want you to notice about this is what's changed our x-intercept? Absolutely nothing. So what does that mean with respect to our Km? Well, our Km is largely unchanged. Now I want to go ahead and make a chart up here and keep track of my Km and my Vmax. So my Km for a non-competitive inhibitor, I'm going to put a dashed line to indicate that nothing happens. My Vmax, on the other hand, what happens to my Vmax? Well, we have a y-intercept when no inhibitor is present. We also have our y-intercept for when a non-competitive inhibitor is present. And what you notice is that when the non-competitive inhibitor is present, the y-intercept increases. But remember, this is a reciprocal value. So that means my Vmax is decreased when a non-competitive inhibitor is present. Okay, so that's a non-competitive inhibitor. Now, I'd like to contrast that with, and I'm going to draw it in blue, the impact that a mixed inhibitor is going to have. What's a mixed inhibitor going to do? Well, keep in mind, I'm looking at a blue line versus a red line here on my double reciprocal plot. And I've drawn this not as straight as I'd want it to, but there we go. It shouldn't have that kind of curve to it, but here we are. So what I want you to notice about this is we have an intersection between our data lines, our no inhibitor or our plus mixed inhibitor. And that happens in quadrant number 2 of our X and Y plane. So that happening in quadrant number 2 is significant because we've seen that line intersect before. The no inhibitor plus an inhibitor, that's a hallmark of a competitive inhibitor. What we also see is that our slope has increased. So the slope increasing is also a common feature of a competitive inhibitor. But I think the easiest thing to do is really just look at, well, how do my axes change? How do my intercepts change? The one thing that I want you to notice right off the bat is that my x-intercept, that value has gotten closer to 0, and therefore that value has decreased. So my Km, in fact, has increased. My Km has increased, which really is a hallmark of a competitive inhibitor. Okay. Now, the other end of this data shows a new y-intercept. Because if you remember a competitive inhibitor, you see the Km go up and the Vmax remain the same. Well, in my rendering here, I show that my y-intercept has gone up more than that of the non-competitive inhibitor. And if you remember, with a non-competitive inhibitor, our y-intercept value increases, therefore our Vmax decreases. Well, in a mixed inhibitor, your y-intercept value increases, therefore your Vmax value decreases. Okay, so the takeaway of all of this is from a perspective of what does this inhibitor do? Well, it's capable of binding the free enzyme. It's capable of binding the enzyme substrate complex, whether we're talking about a mixed or a non-competitive inhibitor. Now, to differentiate between these molecules, the question becomes, well, what is it doing? What is it doing to our kinetic parameters? A mixed inhibitor is going to cause your Km to go up and your Vmax to go down. So it has facets of both a competitive inhibitor and an uncompetitive inhibitor. So features of a competitive and an uncompetitive inhibitor, hence the mixed description. Whereas a non-competitive inhibitor, this is an inhibitor that is going to bind to another site, somewhere other than the active site of our enzyme. So our Km for this is not going to change, despite the fact that it could bind to your free substrate. The Vmax, on the other hand, the Vmax is going to be decreased. So both of these are capable of decreasing the maximum velocity that the enzyme catalyzes the reaction, but they're not necessarily both going to have an impact on the affinity that your enzyme has for its natural substrate. Well, I hope this was helpful to compare and contrast a Lineweaver-Burke plot for a mixed or a non-competitive inhibitor, along with a competitive and uncompetitive inhibitor. All right. Well, thank you very much and have a good one.